Our next topic is about a very important law that helps us to quantify the forces between charges, and it is the Coulomb's law. Now, we've realized that charges exert forces on other charges. So if there are two positive charges, then they will push each other away. That's a force. If there is one positive charge and one negative charge, then they will try to pull themselves together. That's another force. If there were two negative charges, then they will push themselves away, according to the property of charges that we discussed already. What we are going to do today is to rather quantify if there is a force existing between two charges. How strong is the force? And that's what we are going to talk about, is the Coulomb's law. Without wasting my time, let me state the Coulomb's law, then we analyze it. The electrostatic force between any 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance separating their centers. So we have two charges. For an example here, there's one charge with a charge big Q and another charge with a charge small q here. If they are both positive or they are both negative, then they will start pushing, they will push each other away. The small q will experience a force that will try to move it away from the other one. Likewise, the big Q will also experience the same force that will try to move it in the opposite direction. Now, these two forces are the same, and we want to find it. Coulomb's law is telling us that this force is strong if the charges are very big. So, if we have a big charge here and another big charge here, then the force will be big. If we have this charge maintained and we increase this charge, this one has increased, so we are going to have a bigger force. So the first part of the law states that the force is strong if the charges are also strong. Straightforward. Now, the law is also telling us that the charge will be strong if the charges are closer to each other. That's what we mean by inversely proportional. That means if it's inversely proportional, then it means as the denominator gets bigger, the force becomes smaller because we are dividing by a larger distance here. Then the force will become much smaller. So if the distance, if they are very close to each other, then the force between them will be very, very strong. That's what we mean by inversely proportional. In other words, as the charges separate, the force becomes weaker and weaker. But as the charges get close together, where the distance becomes smaller, then the force between the charges becomes stronger. So this is all that Coulomb was saying. Let's move on to see how we can apply Coulomb's law. Even before then, let's talk about the mathematics. Now, if we have a proportionality relationship, for example, the force being proportional to the product of the charges and inversely proportional to the square of the distance separating their centers, we can change the proportionality and make it equation by introducing a constant of proportionality. That is what we often refer to as K. K in a vacuum, in a free space, will give us a value of 9.0 by 10 to the negative 9 Newton meter squared per Coulomb squared. So that will be the value of K. It is a constant. unless we change the medium in which the charges are. If the charges are in oil, then this epsilon, which currently has a value of 8.85, will be different. This epsilon, this value here is for free space or vacuum. So if the charges are found in vacuum, then we use this epsilon. That will give us, that will make K 9.0. If epsilon, if the charges are in another medium like oil, they are in water, or they are in other medium, then that medium will have different permittivity of free space. This value epsilon is called the permittivity of free space. It has a value of 8.85 times 10 to the power negative 12. So if we substitute it in the expression for K, then we are going to get this. So very often you simply have to quote this K and you are done. Quote it, place it there, and you'll be able to work. Let's take an example. Two identical conducting small spheres are placed with their centers 0.300 meters apart. One is given a charge of 12 nanocoulomb, and the other is given a charge of 18 nanocoulomb. Please, this N is nano. Nanocoulomb is a multiplier. You can read about that. There are two questions for this preamble. Find the electric force exerted on one sphere by the other. So I've represented the story here pictorially. One way you can succeed in solving problems is to try to present the problem in a picture form. Then it will help you. Your chances of getting the answer will be very, very bright. Alright. So we have one charge here having a charge of 12 nanocoulomb and another charge here having a value of 18 nanocoulomb. So this one has a higher positive charge than the other one. Now we are asked to find the force between them. You should realize immediately that because the charges are positive, they will be repelling each other. Okay, so that's easy to realize. But how much force would they be repelling each other? That one you need to calculate. You can't just speculate and think that, okay, I think it will be something like that. No, we have to calculate, and Coulomb's law is going to help us calculate. Let's see what happens. First of all, you can write the formula that applies. So we have one charge multiplied by another charge divided by the square of the distance separating them. Let's put everything in. The constant is here 9.0 by 10 to the power 9 multiplied by the first charge, which is 12 nanocoulomb. When we say nano, it is 10 to the power negative 9. When you see nano, micro will be 10 to the power negative 6. Milli will be 10 to the power negative 3. Okay, so when we say nanocoulomb, then we are talking about 10 to the power negative 9. So the first charge is 12.0 times 10 to the power negative 9. And the second charge was, the second charge was 18 nanocoulomb divided by the distance separating them, which is 0.300 squared. If you strike everything, it's possible I made a mistake here. You can correct it. Just point these ones in your calculator and correct the value here. We are only trying to say that there is a certain force that is pushing these two charges off, and that if you do it correctly, you get the right amount of force that is pushing the two charges apart. Now, the second question is very interesting. I included this question to help us recall what we've done earlier, or what we've spoken about earlier, and also as a form of practice. It helps us consolidate what we've learned so far. Now, the question is asking, the spheres are connected by a connecting wire. I've indicated an arrow here that is showing a connecting wire. This wire itself is a conductor. Remember, the question itself was talking about two particles. So we've now conducted the charges, one from the other one. Okay. And remember, the particles are also conducting small spheres. They are conductors. That means charges move freely in them. And the wire here is also a conductor, so charges can also flow easily through them. The spheres are connected by a conducting wire. Find the electric force between the two particles after equilibrium has occurred. Yes, it is giving us a clue already that equilibrium will occur. Now, why do we have 12.0 nanocoulomb and we have 18 here? The two spheres are similar. They are similar. That means initially they had equal number of protons and electrons. This one has 12 nanocoulomb because it has more electrons than this one. This one, more electrons have been removed from it. That's why there's a greater positive charge on it. So this one will have more electrons than this one. You see, that means this one is deficient of more electrons than this one. If we should connect these two together, because this one is more positive, it will pull some of the electrons. It will attract some of the electrons to the side. And that pulling will continue until this one also grows in positive charge and try to stop the runaway of the electrons. So the difference in charge here will be about 6. If we subtract 12 nanocoulomb from 18 nanocoulombs, we are going to get excess of negative 6 nanocoulomb. That's the number of electrons in excess here, not in excess per se, but there is 6 nanocoulomb electrons here than there is in the other one here. So this 6 nanocoulomb will be shared between them. You see, this one will not give everything to this one. It will give some until they are par. So if they share it half-half, that's a 3 nanocoulomb goes to this one. This one reduced to 15 nanocoulomb. And this one losing some electrons to this one will also increase in the positive charges because it has lost more electrons, so its positive charges will now increase to 15. So there is 15 coulombs here, there is 15 coulombs here. So that will be the equilibrium state. You can now use Coulomb's law to find the electrostatic force of repulsion between them. They will still be repelling because this one will be 15 nanocoulomb, this one will also be 15 nanocoulomb. And you can strike the value itself. Okay. Now, our third objective is to appreciate that Coulomb's law is not applicable to every situation. All that we've been talking about are about point charges. That's particles that can be considered as points in space. So there is a sphere, there is another sphere. Look at the distance between them. It's very, very wide compared to their sizes. So we can assume this sphere is a point charge. It's like it is being considered as a point that is carrying charge. Then there is another point that is carrying charge. So Coulomb's law applies to this situation only. Look at other situations that Coulomb's law cannot apply. There is a long wire here on which charges are distributed. This wire is charged. And this sphere is also charged. So somebody will start thinking about the force between this long wire and this sphere. There should be another way of finding the force that is attracting this long wire to this sphere. We can use Coulomb's law to find that force there. Indeed, it's not part of our course now, but I just want you to appreciate that Coulomb's law cannot be used in all situations. It is used for point charges only. Okay, there is another situation here. We have a sphere in the middle and there is a ring. The sphere is charged, the ring is also charged. We can use Coulomb's law to find the force of attraction or repulsion between the sphere and the ring, because even if we consider the sphere to be a point charge, the ring cannot be considered as a point charge. Then the third one, we will delve deeper into it because we are going to talk about capacitors, will be two plates. If this plate is charged and this plate is also charged, you must start thinking, what will be the force of attraction between these two different charges? We can use Coulomb's law to do that. Maybe another formula will work, but Coulomb's law will not be able to help us to calculate the force of attraction between these two plates. So again, we want to state that Coulomb's law applies only to point charges where we have point and then another point carrying charges, either they are of the same charge or of different charge. Alright, so this is what we have for now. We come back to consider electric field.